Narrator: have you ever looked up at the night sky and felt a sense of wonder? Narrator: a feeling of profound smallness in the face of such vastness? Narrator: hidden among those brilliant twinkling stars are secrets of an entirely different nature. Narrator: they are not points of light, but points of absolute darkness. Narrator: these are places where the universe as we know it simply stops. Narrator: they are riddles wrapped in the fabric of space-time itself. Narrator: objects so extreme, so utterly bizarre that they challenge our deepest understanding of reality. Narrator: what would happen if you could visit one? Narrator: what would you see? Narrator: the answer, quite wonderfully, is both nothing, narrator, and everything, narrator, all at once. Narrator: these cosmic enigmas are called black holes. Narrator: they are not empty spaces, but rather an immense amount of matter packed into an impossibly small area. Narrator: imagine squeezing a star many times more massive than our own sun into a sphere just a few kilometers across. Narrator: the result is a gravitational field so powerful that nothing, not even light, can escape its clutch. Narrator: this is why we call them black. Narrator: they are the universe's ultimate trapdoors, one-way journeys from which there is no return. Narrator: they lurk in the darkness, silently waiting, bending the very light that dares to pass by them. Narrator: to understand a black hole is to grapple with the limits of physics and imagination. So what exactly is a black hole? Let's break it down. It is not a hole in the traditional sense. It is a region of space-time with extremely strong gravity. That means nothing can escape it. No particles, no light, no information. This boundary of no escape is the event horizon. Think of it as the edge of a waterfall. Upstream you can paddle away. Cross the edge, no return. Where do we find them? Everywhere. Astronomers think there are millions, perhaps even billions of stellar mass black holes in the Milky Way alone. These smaller ones are a few times the mass of our sun. They roam the galaxy like silent predators. They emit no light, so we spot them by their effects on stars and gas. But there's another, much larger kind. Black holes are not born in peace. Their creation is one of the most violent events the universe has to offer. The most common type, the stellar mass black hole, is the final, dramatic endpoint in the life of a very massive star. A star is in a constant battle with itself. Nuclear fusion in its core creates outward pressure, pushing against the immense inward crush of gravity. For billions of years this balancing act holds, letting the star shine steadily across the cosmos. But all stars eventually run out of fuel. For a truly massive star, at least 20 times our sun, the end is catastrophic. When nuclear fuel is exhausted, outward pressure vanishes. Gravity wins in an instant. The star's core collapses with unimaginable speed. The collapse is so violent it triggers a titanic supernova, an explosion that can briefly outshine a galaxy. Outer layers are blasted into space, enriching the cosmos with heavy elements, while the core keeps collapsing. If the remaining core is roughly 3 times the sun's mass, let's imagine for a moment that we could take a trip to a black hole. What would it be like as we approached? From a safe distance, the black hole would be invisible, a perfect circle of blackness against the backdrop of stars, but its presence would be unmistakable. The light from the stars behind it would be bent around its edges, a phenomenon called gravitational lensing. The star field would appear warped and distorted, like looking through the bottom of a giant wine glass. This is space-time being curved by the black hole's immense mass. As we get closer, stranger things begin to happen. The gravitational pull is not uniform. The part of our spaceship closest to the black hole would be pulled much more strongly than the part that is farther away. This difference is called a tidal force. For a small, stellar mass black hole, these tidal forces are extreme. They would stretch our spaceship and us like spaghetti. The name for this is spaghettification. We would be pulled apart atom by atom. One of the most mind-bending consequences of Einstein's theory of relativity is its effect on the flow of time. Gravity warps space, but time as well. This effect, known as gravitational time dilation, means that time runs slower in a stronger gravitational field. This isn't just a theoretical idea, it's a measurable fact. The GPS satellites orbiting Earth have to constantly adjust their clocks because time for them runs slightly faster than it does for us down here on the surface where gravity is stronger. Near a black hole where gravity is taken to the absolute extreme, this effect becomes profound. Imagine you are in that spaceship, hovering just outside the event horizon, while I watch you from a safe distance through a powerful telescope. For every minute that passes for me, only a few seconds might pass for you. Your clock would appear to me to be ticking incredibly slowly. If you were to spend an hour near the black hole and then return, you would find that decades or even centuries had passed for me and the rest of the universe. From my perspective, as you get closer and closer to the event horizon, your journey would seem to slow down. Your image would become redder and dimmer. For a long time, black holes were purely theoretical objects, fascinating mathematical curiosities in Einstein's equations. But, we now have overwhelming evidence that they are real, and we've even identified many of them. Perhaps the most famous is the one that resides at the very center of our own Milky Way galaxy. It's called Sagittarius A, pronounced Sagittarius A star, and well, it is a true cosmic monster. It has a mass of about 4 million times that of our Sun, all contained within a region smaller than the orbit of Mercury. We cannot see Sagittarius A directly, of course. It's hidden from our view by thick clouds of gas, thick clouds of dust, and by its own nature as an object that emits no light. So how do we know it's there? We watch the stars around it. For decades, astronomers have been tracking the orbits of stars very close to the galactic center. These stars are moving at incredible speeds, some traveling at several thousand kilometers per second. They're whipping around a central point that is completely dark. The only thing that could command such loyalty and speed is an object of immense mass and gravity. A supermassive black hole. In 2019, humanity achieved something truly remarkable. Why are scientists so fascinated by black holes? Why do we spend so much time, effort, and resources studying these dark, distant objects? Black holes are the ultimate laboratories for testing the laws of physics. They're places where our two great theories of the universe are forced to meet: general relativity, the very large, quantum mechanics, the very small. And right now, those two theories do not agree. General relativity works on large scales, from the orbit of the Earth to the bending of starlight around a black hole. Quantum mechanics rules atoms and subatomic particles. At the singularity, mass crushed to a quantum-sized point, both must apply yet give contradictory answers. This tells us our understanding is incomplete. There must be a deeper, more fundamental theory, a theory of everything. Black holes are crucial to how the universe works. Material swirling into a supermassive black hole forms an accretion disk. The disk heats from friction and emits enormous energy. That emission makes quasars, some of the brightest objects in the universe. We've learned an incredible amount about black holes. We know they are real. We know how the stellar mass ones form. We've measured their masses and even photographed their shadows. We understand their powerful effects on space-time, on light, and on the flow of time itself. We've detected the gravitational waves, the ripples in space-time that are produced when two black holes merge. These discoveries represent some of the greatest triumphs of modern science, confirming predictions made a century ago and opening new windows onto the cosmos. Yet for all we know, the list of what we don't know is perhaps even longer and more exciting. The singularity remains a complete mystery. What actually happens at that point of infinite density? Do our laws of physics truly break down, or do we just need a new, better theory to describe it? Black holes are more than just cosmic curiosities. They're a fundamental part of the universe's past, present, and future. They are the final resting places of the most massive stars and the powerful engines at the heart of galaxies. They bend light-warp time and challenge the very foundations of our understanding of reality. They represent the frontier of human knowledge, a dark shore against which the waves of our scientific theories break. What we've learned about them has already transformed our vision of the cosmos. The journey to understand these objects is a testament to human curiosity. It's a story of how we can sit here on our small blue planet and reason about the most extreme and distant objects in the universe. From Einstein's equations scribbled on a notepad to a globe-spanning telescope capturing an image of a galactic monster, it shows what we can achieve when we work together to ask big questions. The study of black holes pushes our technology, our mathematics, and our imagination to their absolute limits.